Okay, my BC kids, I'm going to try to give you a shortened version of slope fields, section 9.2. So we're looking at differential equations in section 9.1, and it's all well and good when you can solve them out, but sometimes you're not going to be able to. So that's where there's a graphical way using slope fields to be able to solve differential equations. And that's what this is about in this section. You saw this back in AB. So hopefully it wasn't too far from where you've been. But a slope field or a directional field is a graphical general solution to a differential equation. To create the slope field, all you need to do is to plot short line segments that demonstrate the slope at a particular point. And then that gives you kind of a feel for how the graph is going to go. So example 1, they say in the diagram, plot the slope field. And you say, okay, well, it's 2y is the equation. So what you need to do, and I put a little table off to the side here, you need to, it's all based on the y values. You don't care what the x values are for this particular one. So if y is negative 2, then negative 2 times 2 is negative 4. All I'm doing is plug it in here. If y is negative 1, then I get negative 2. If it's 0, I get 0. If it's 1, I get 2. If it's 2, I get 4. There's my plot. Okay, so what I'm going to do is come over here, and everywhere that y is 2, negative 2, that's down here, I have a slope that's negative 4. So what I'm going to do is put little short lines that show an approximate negative 4 slope. All right, no big deal. At 1, when I'm sorry, I'm here at negative 1. When y is negative 1, I get negative 2. So it's not as steep as it was down here. So let me make it a little smaller there. If it's 0, it's 0. Well, that's easy. They're just straight across. If it's 1, it's 2. So now I'm in a positive direction. If it's 2, it's 4. There you go. You plotted the slope field. Suppose that you know that the point 0, negative 1 is a particular solution on this particular differential equation. By following the slopes, draw the diagram on the diagram what you think the particular solution would look like. So I've got a coordinate at 0, negative 1. So here it is. And all you need to do is kind of follow these. I call them like cattle chutes. They remind me of cattle chutes. Like if you were trying to herd a bunch of cattle, you would be following them, so you would be going this way, but you can't go past the 0, right? It would have to keep asymptoting along the way. And on this side, it kind of can keep going down to negative infinity. So there it is. Solve the differential equation, part C, by separating the variables. All right, this goes back to what we did last section. If I've got my function, my differential equation, is y equal, or dy over dx, my derivative is 2y. Then I'm going to get the y's on one side, the x's on the other. I end up in the ln worlds, which means that I have to change it into an e. So I'm going to do my loop-de-loop. I get e to the 2x plus c equals y. Interestingly enough, they oftentimes break this apart, because remember, if you're adding exponents, it's like multiplying. So this would be equivalent to e to the 2x times e to the c, which, think about this for a minute, what is the value of e to the c? It's some constant. I don't know what it is, but it's some constant, right? It's not going to change that that's a constant. So this e to the c piece becomes this capital C constant in front of you being multiplied by your e to the 2x, and that's your general solution. And then they told you you've got a particular solution at 0, negative 1. So if you plug in your 0, negative 1, x is 0, y is negative 1, you end up with being able to solve for your actual function itself. And that is y equals negative e to the 2x. And so that was your example 1 problem with slope fields. Let's see what else we got. Same idea with example 2, except example 2 has now a bigger, badder differential equation slope field here. You've got x's and y's involved. And so what I did was I took all of these, 1, 2, 3, 4, I took all 12 of them and put them into a table so that I could figure out what that what the slope field would look like. So here's my table work for all of that. That's sketch the slope field. And then part B says find the particular solution. So I've got to separate the variables, and then I need to integrate both sides. This one, when you integrate, you end up with a cube root, which is here. And then plug in your -1 for y, your 0 for x's. You can solve for the actual c value, which gives you the perfect function for what this would be. And then they told you that there's a magical way through Desmos to be able to graph these. And I don't know if you got a chance to try it, but if you put in your search engine Desmos slope fields, right here, even if you put in what they told you, Desmos slope field generator, oh my goodness, it's a lovely thing. So you can actually have it generate for you what the graph would look like of the slope fields. So that's what they did in example 3. Then they gave you some particular solutions, but you didn't necessarily, I mean, I did the work by hand down here to figure out what each one of them would be. Here's my separation of variables, my whole ln thing that has to turn into an e, so e to the negative sign of x plus c equals 3 minus y, so I did my whole loop here. And then remember, if it's e to the c, that's just a constant in front. That's this guy. And then I went from there to solve for y, so I just brought the 3 to the other side, kind of flip-flopped things around a little bit. And then I did all my work for figuring out these 5 different specific equations based off of the initial point value that they gave me. So I showed all the work for all of those and all this stuff, but you could have done this through the slope field generator on Desmos, so that would have been an option too. Alright, there's example 3. Here's the graphs of all those things. So if you're looking at what the picture would be, remember the only thing that's different about them is their vertical placement. So that plus c at the end, remember the plus c as you integrate, just changes the vertical location of whatever it would be. So here's the 5 graphs, right, of the 5, what they would look like based off of those different c values. That's the picture. And then the rest of these were matching. So if you think about it, match the general solution. Well, if I'm y equals 1, I'm a horizontal line. I kind of went through these and was like, let me think about what these would look like. If I'm y equals x, I'm a straight line like this. If I'm x squared, of course, I'm a happy parabola. I'm cubed. And 1 over x squared, I'm a sine graph, I'm a cosine graph, and I'm an ln of the absolute value of x. Well, which picture, if I were to stay in the cattle chute, which picture does this one look most like? And that would be your sine function, because it goes through at 0, 0, and you can see the wave of the sine function. If I'm looking at this one and I stay in the cattle chute, I can tell that it's going down towards -infinity, and then it does some kind of a switch and turns up. So I can see that it looks like it would be a cubic function of some sort. So this one matches with F, that one with D. And then match these slope fields with the differential equations. This is a little bit harder. So you're looking for, I always look for places that would be zeros first. Like for example, I know that in Roman numeral number 1, e to the x, if x is 0, what are all of the answers for this going to be? Anywhere x is 0, you're going to have a y that's 1, right? Your value is going to be 1. So you want to find the graph where that happens, where when x is 0, all of your y's are 1. And you can see that that does happen with this guy. If I'm at x equals 0, everybody's got the same exact slope values going on. This one, it's undefined when y is 0. So the only one, if I look at where it's undefined, when y is 0, that means it's a vertical slope field line. And so a vertical slope field line would be this one, C. So you're trying to eliminate things based off of parts that you might know. So like if you have a fraction, check out the denominator and see what's going to cause that to be 0. And then make sure that you have vertical slope field lines at that place. And the rest is just, it's kind of trial and error. Try some points here and there. You kind of know which one's the sine function, right? Which one has the wave. That would be this guy. So there are some process of eliminations that you can try to help narrow down the field. These are a little bit tricky. I have seen questions where you're matching slope fields on the actual exam. And that's it for examples. So you're set to try the homework problems. They are matching and finding differential equations, like solving for differential equations. There's only five questions. They're not that long. Okay, that takes care of section 9.2, but we'll talk more in class when we get together to clear up any other questions that you might have. All right, I'll see you soon.